Alright, hi everyone, welcome to my YouTube channel, City of Elections. So still working on the past questions, communication systems, still working on the past questions. Now, look at this. So with the aid of a diagram, it illustrates the spectrum of a message signal and the corresponding AM signal. Now, what you need to bear in mind first of all, so what we are dealing with is AM signal spectrum, okay? So, amplitude modulated signal spectrum. First thing first, what is a spectrum? When you hear spectrum, what should come to your mind? Now, a spectrum is the entire range of frequencies that make up any wave, sound, light, radio wave, etc. Okay? The entire range, that is from, this is frequency. Okay, this is for frequency. Okay, this is for frequency. And then this is for amplitude. Okay, amplitude. Now, the entire range is what we refer to as spectrum. So, the spectrum of a message signal will show all frequencies of that message signal. Okay, so we'll now have it like this: frequency for message signal, and then let this be the message signal. Are we seeing it now? So this is what we have here. It's just like what we have here. Okay, so I think there should be M here. So frequency for the message signal. Okay, left side band and right side band. Okay, band. All right. Then, so this is for the spectrum spectrum of the message. Okay. Now, that means we have done the first part by doing this. Illustrate the spectrum of a message signal. That's this part. Now, and the corresponding AM signal. Now, when we say AM signal also has its own spectrum. Okay, it also has its own spectrum. I think I should take this other part, but let me just quickly do that here. So the AM signal also has its own what? Spectrum, which is the carrier signal. So positive, and then what? Negative. Okay, the amplitude modulated signal also have its own spectrum. Now, since we are encoding the message signal, because that's what we do, and that's the idea of modulation, you encode the message signal into the carrier signal. If you encode it into its amplitude, then it's amplitude modulation. So since we are doing that, that means we are going to have this message signal, this message spectrum, we are going to have it inside the carrier spectrum. So look at it here. I already have it here. So this is the carrier spectrum. Are we seeing it? Then we now have the message spectrum inside the left hand side of the carrier. The same message inside the right hand of the what? Carrier. Are we seeing how simplified this thing is? So what you have here is everything you have. Let me write this thing again. Okay, so the next thing is PAM demodulation, which is of course still past question. Now, briefly explain demodulation in pulse amplitude modulation with the aid of a diagram. First thing to bear in mind is that all we are talking about, demodulation, PAM, pulse amplitude modulation. Now, all what this means in simple terms is just the process of extracting original signal from a sampled pulse-based signal. See, get back what you modulated. We talked about we talked about this. Okay, we talked about this in the previous video, like I think before this, that you want to get somewhere and and you enter a bus. When you get to the destination, you will leave the bus, you will exit the bus. Okay, so just think of it as getting into the bus so that you will be carried from this point to the other point. Getting into the bus, think of it as modulation. Getting out of the bus is demodulation. Okay, so encoding the signal, encoding our message signal is modulation. Okay, and the process where we encode the message signal into either the frequency or the angle, okay, that's the phase, or to the amplitude, that's the modulation. That's modulation. Then demodulation is to get back our message signal. Okay, so that's just the basic idea, and we're asked to explain it and then use a diagram also. So to carry out this demodulation, we use a low pass filter. Note that most message signals are of low frequency. So a low pass filter allows low frequencies to pass, just like the name. Okay, so when we take this signal through low pass filter, it eliminates high frequencies. Okay, so high frequency ripples, it eliminates high frequency ripples and generates the demodulated signal, which has its amplitude proportional to the pulse amplitude modulated signal at all time instants. What that means is that when we pass our, look at this diagram here. So this is a signal, okay, which has been modulated. So it contains both high and low frequency. That is, it contains the carrier signal, high frequency, and then the low frequency, which is our message signal. So when we pass this through the low pass filter, only the low frequencies will pass through. So what we'll get out of it is what? The demodulated PM signal. Think of it as having a filter. You have a filter or a net, something like that. You have a net, you have a net. Think of it like that. Let's make it smaller. Now, if you pour in, let's say, stones or things like that, only the smaller size will go through this thing. The bigger size of stone or whatever, the bigger size will not go through it. So it will only allow the low pass, the small size to go through. So this filter, okay, when we do that, okay, this filter will allow the smaller stones to go through. That is a small stone filter, okay. But in this case, a low pass filter, which allows only low frequency to pass through. So at the end, let's say we pass, okay, we'll pass it like this. At the end, what will come out? Only the smaller stones, which we are interested in. I'm just using that as an example, okay? Okay, so that's just all for this part. Okay, so the next is effect of multipath fading. Okay, so now from the past question we have that what is the effect of multipath fading on the observed received power at the receiver? Now, first of all, what's the idea of multipath fading is this. Okay, multipath fading occurs, okay, when signals from a transmitter reach the receiver via multiple paths due to reflection, diffraction, and scattering. That is, let's say this is the destination, okay, receiver, and this is the receiver and transmitter, okay. Now, we have a signal coming from this guy. Now, when we have it as maybe, okay, due to reflection or something, then we have the signal being scattered all over, okay. So this action or this phenomenon, now it will lead to different things, okay. That means the power from the sending end will not be the same as the power at the receiving end, okay, because the signal from a transmitter reach the receiver via multiple paths, different paths, due to what? Reflection, diffraction, and scattering. So the following are the effects of multipath fading on observed received power at the receiver. So when we have this multipath fading, so what are the effects? The first one is signal attenuation. Of course, attenuation just means reduction in signal strength. So reduction in signal strength. So this multipath fading will lead to reduction in your signal strength. And then time dispersion. So this means that due to this path, multi-paths, okay, the signal may delay, and it may lead to different time delays in a particular signal from one particular signal to the other, like comparison of different signals sent from the transmitter to the receiver. So it will lead to this multipath fading will lead to time dispersion. Also Doppler shifts, and of course this is when there is relative motion between the transmitter and the receiver. Okay, maybe of course transmitter maybe stationary, but you the receiver with your phone, maybe you are moving or maybe running or in the bus, okay, in car or something. Now when there is relative motion between the transmitter and the receiver, this Doppler shifts occurs. And have you noticed when maybe a car is driving towards you, and you hear or maybe siren, and you hear it coming towards you? It usually comes at a very high pitch, and when it gets to where you are, it's like the frequency changes from high frequency to a low frequency. Coming towards you, it sounds like high frequency. Then going away from you, it sounds like lower frequency. Then the next effect is error rate. So these signals being transmitted, they are in bits. Okay, so due to this multipath fading, it may lead to increase in bit error rate. Okay, increase in bit error rate, and that's really significant when we talk about digital modulation schemes. Then the last one is frequency selective fading. Now the multipath fading can vary with frequencies. Okay, so a certain frequency may have a certain multipath fading, another frequency may have another multipath fading. Now this will now lead to different levels of attenuation. Okay, now when it leads to different levels of attenuation, this frequency selectivity can cause different level of attenuation across the frequency spectrum. We talked about spectrum some minutes ago. So for that reason, it appears like selecting different frequencies. So different frequencies will have their own level of attenuation. This frequency selectivity, of course, it will cause distortion. It can cause distortion and in the received signal, and of course affecting the quality. Okay, so that's for this part. Okay, so the next is characteristics of radio receivers. So what are the characteristics of radio receivers? We are asked to describe 5 characteristics. Now, here, so these are the following. Okay, now these are some of the characteristics: selectivity, fidelity, noise figure, double spotting. What does all this mean? Now, this here is just in simple terms. Okay, so for selectivity, what that means, for a radio to be selective, the property or characteristic selectivity of a radio receiver is its ability to differentiate desired signal from unwanted signal. That is as simple as it is. Okay, the signal we need and the signal we do not need, the signal we want and the signal we do not want, the radio's ability to select, to differentiate. So that's what we mean by selectivity. In general, the higher the gain of a receiver, the better its sensitivity. Okay, now the next characteristics is fidelity. And when we say fidelity, it just measures, it's just a measure of the ability of a communication system to produce an exact replica of the original source information at the output of the receiver. So then the next characteristics is noise figure. Noise figure is just the amount of noise an element adds to the overall system. Note that noise is an unwanted signal. It's still a signal, but it's unwanted. Okay, so the amount of noise an element adds to the overall system. The lower the value of noise figure, the better the performance. I guess that's obvious. The last property or characteristics is double spotting. And it's a condition where the same desired signal is detected at two nearby points on the receiver tuning dial. One point is the desired point, while the other is called spurious or image point. Okay, so when you tune your dial, the receiver, radio receiver, you observe that the signal you want, you can see it, you receive it in a particular point, and then you can also get, or you observe that there is a signal like almost the same as the one you are looking for on a nearby point. So that's just double spotting. It sounds like the name. Okay, so that's that for this part. Okay, so the next one is this, which is the super heterodyne AM receiver. Now, this is the past question here. With the aid of a diagram, briefly describe the working principle of a super heterodyne receiver. Now, for this receiver, here we have the diagram here. Okay, so for this receiver, it receives, the receiver converts all incoming signal. Look at it, incoming signal. Okay, so this is the wave, and then receives through the antenna. So incoming signal. Now it converts all incoming signal into lower frequency known as intermediate frequency, IF. So you can see it here, IF. So it receives, and then you can see this IF here, plus or minus B over 2 kilohertz, where B is this 10 kilohertz for AM and 200 kilohertz for FM. Okay, now so it converts all incoming signals to a lower frequency known as intermediate frequency, at which a single set of amplifiers and filters is used to provide a fixed level of sensitivity and selectivity. Now, the amplifiers and the filters, this is what we have here, amplifier, and this is a filter, amplifier and filter. So this set is used to provide a fixed level of sensitivity and selectivity. So most of the gain and selectivity in a super heterodyne receiver are obtained in the IF amplifiers. This is the IF amplifier, right? IF amplifier. So most of the gain is obtained here. Now the key circuit is the mixer. Mixer here, which acts as a simple amplitude modulator to produce sum and difference frequencies. Okay, acts as what? Frequency modulator. Now the incoming signal is mixed with a local oscillator signal to produce this conversion. Look at the local, this is the local oscillator Okay, signal. So this is, look at the incoming signal, then a local oscillator. You see they are mixed here, okay, mixed here, and then of course the intermediate frequency amplifier. Now that is demodulated, and then you have your audio amplifier and then output to speakers and the speaker. So this is just how that stuff is. Okay, so I think we'll stop here for now and then continue the rest part of the past question in the next video. So just stop here for now. All right, thanks a lot for watching. Like, share, subscribe, and I'll see you in the next one.